purpose of diode is as a rectifier. That is the main purpose. That is converting AC voltage to DC voltage. This is symbol for AC voltage, correct? That means no plus minus AC voltage. My voltage is varying like this. We'll take one cycle. This is positive, negative. During the positive cycle, anode is positive. This is anode, this is cathode. So this is positive, this is negative during this entire cycle. In that case, already as you told, the voltage is increasing with 0 volt, increasing sinusoid. For example, the peak voltage is 5 volts. For example, I say that it varies the V peak positive equal to plus 5 volts. V peak negative equal to minus 5 volts. And it starts from 0. As the voltage increasing 0.1, 0.2, 0.3, the current will not flow. Diode is not forward bias. Now, once the current reaches, for example, 0.7 volts, after some time, the diode is automatically current will start flowing. IDC will go. Now, this voltage will become 0.7 volts. Correct? Now what is happening? 0.7, 1, 2, 2, 3, 4, 5. Correct? So this voltage is increasing. The supply voltage increasing up to 5 volts because the positive feedback. But if you measure, you connect a voltmeter across the diode like this, plus minus, this is my voltmeter. What will show? 0.7 volts. When the input voltage V in or AC, positive half cycle, is varying from 0.7 to 5 volts, this input is increasing. But if you measure the voltage across diode, since diode is conducting, which is called a cut-in voltage. Correct? Positive side is okay, fantastic. Okay. Your question, what I want to, you want to do, when you apply negative, what will happen? During positive half cycle, anode is positive, cathode is negative, above 0.7 volts. So the current ID is flowing. Correct? ID equal to, we know that V supply minus V diode. What is V diode? V diode equal to 0.7 volts once it is conducting. So if, for example, if voltage input, this location, this is 3 volts. At this time, insert Vs equal to supply voltage is 3 volts minus this voltage above 0.7 volts, 3 volts. Automatically diode voltage will be 0.7 volts. This is the voltage across, what you call differential voltage available. That is what is going to supply a current cycle, which is not. Now, during negative half cycle, anode will become negative, cathode will become positive. Now we know the same diode reverse bias. This diode during the negative half cycle, this cycle, correct? Anode is negative, cathode is positive, reverse bias. Your question on Zener breakdown, fantastic, nice thing you are observing. I am very happy about it. What happens? If you apply reverse bias, the current cannot flow. Current diode is not conducting. But there will be a current ID, reverse bias current, ID reverse bias current will be there. That will be in the order of microvolts, amps or nano amps. 10 power minus 6 to or 10 power minus 9 generally range. Theoretically, what should be I reverse voltage? Anybody? What is the IDC? Diode current equal to V supply minus V diode current divided by RD. RD is called as dynamic resistance of the diode. What is dynamic RD? When reverse bias condition? In reverse bias condition, it is infinity. Correct? Practical, it will be 10 power 6 to 10 power 8 or 10 power 9 ohm. This is megohms. 1 megohm, 10 megohm, 100 megohm, like that. Okay. So that means now if I apply this formula, it is not infinity, practical diode. I say, for example, I take 10 power 6 ohms. So what is the supply voltage I am giving? For example, I am giving a peak. When the sinusoid voltage increasing 1, 2, 3 reached at this time, it is 5 volts, this one, correct? Positive. Similarly, at this time, negative 5 volts. Okay. If you have positive 5 volts, 5 minus during positive cycle, maximum current. maximum current flows, maximum current or diode current is at a peak sinusoidal voltage. That is going to be 5 minus, I said peak value 5 volts minus 0.7 divided by RD. Okay. RD, already told you, in case of forward bias, how much it should be? Forward bias condition, any idea? Theoretically, reverse bias and infinity ohms. Forward bias, how much it should be? Theoretically, 0 ohms. Okay, but practical, it will be in the order of 0.01 ohms to maybe even 10 ohms. 10 ohms. So 10 ohm is milliohm, 10 milliohms. Generally, if you see power diodes, there are two types of diodes I told you. Small signal diodes. Other one is called power diodes. Small signal means the voltage, supply voltage, V supply can be, or whether DC voltage or AC voltage, whose V peak of this one cannot, generally will not exceed 30 volts. D will be in the order of milliamps, less than 1 amp or something. Okay, that is small signals. Power means I told you voltage can be greater than 50 volts, even up to 5,000 volts. That is a high voltage. Current can be 1 amps to even 500 amps. There are diodes, a single diode capable of withstanding 500 volts and 500 amps also. That will be bulkier. The diode will be 10 kg, 20 kg, will be a lot bigger heat sink, all those things. That is called a power diodes, correct? Where the power diode, this one, in forward bias condition, the cut-in voltage is 0.7. If you apply the 5 volts divided by forward bias condition, I told you 5 minus 0.7 is going to be 4.3 volts divided by RD. For a power diode, for easy purpose, I say this is RD equal to 0.1 volts. Forward bias condition, correct? 0.1 volts. Then what will happen? This will be 4.3 divided by 0.1. What is the current? ID equal to 43 amps current will be going when I apply 5 volt supply. Correct? So that means this 4.3 volts, where it is going to get dropped? Any idea? Somebody can tell. I said I supplied 5 volts at peak voltage, sinus 0.7 volt plus this, remaining 4.3.
It will be across the loads.
So this the load voltage, I say VL. What is VL? VL equal to V supply minus V diode at any given instant. Okay, so that can be calculated. How much you can theoretically can calculate. That is the practically how you can compute this voltage across VL. VL can be computed IL multiplied by RL. Correct. This is RL. Load resistance by RL. If you know the current and multiply this one, automatically both should be equal. They both should be equal. This is theoretical calculation according to KVL. This you can measure. This also can compute measure. Okay, this is forward bias condition. Now his question was, if I apply reverse bias condition, what happens? Diode is like this. Sorry, we are talking AC voltage. Very sorry. AC symbol, AC voltage. This is my anode. This is my cathode. During the time negative half cycle, I told you, during negative half cycle, we are talking this period. Right? So this period I'm talking, previously we talked about positive cycle. This is negative cycle. During the anode is negative, cathode is positive. It is connected at a load. Okay. His question was, what about Zener breakdown? You need to select. We know that when I saw the VI characteristics of a diode, I think Monday we saw, or last week, it was something like this, going like this, right? This is nothing but 0.7 volts. This is going to be ID, which is nothing but IL. This is called a forward bias region, FBR. This is called as reverse bias region. correct? So this is 0 and this is going, say for example, it is a 30 volt diode or 10 volt diode, because up to scale I want to show it. Past you can apply only the maximum VD max equal to 10 volts. The diode maker said ID max equal to 1 amps. The manufacturer told, correct? Can be plus or minus 10 volts only. Okay, this is okay. Now, when it goes to reverse bias condition, cathode is positive, anode is negative. Theoretically, there's no current should not flow. No current flowing because it is called blocked condition. Reverse bias condition is also called as blocked condition. Also called as blocked state. BLOCK. That means what it is blocked? Current is blocked. Current cannot flow. Okay. That region is this region, this quarter. Okay. Now, as you increase 0 volts, this is minus 1 volts, minus 2 like this. As it go, this voltage is inner voltage called as breakdown voltage. Okay. The Zener breakdown voltage of the particular diode. I told the diode maximum is 10 volts. Correct? That means it should be able to withstand plus or minus 10 volts. When I apply negative 10 volts also, this should be negative 10 volts. This should be minus 10 volts. This is 0. This is 5 volts negative. And the Zener breakdown of the diode, what you are selecting. I think who asked this question?
Sir, it was me.
Who me means I am not able to.
Andrew.
Thank you. So you have to select the diode whose Zener breakdown is greater than the AC voltage what you are supplying. I said my sinusoid voltage varying between plus 10 volts to minus 10 volts. What you have to see spec is what is the maximum voltage apply in the forward condition. Also, generally that will be same as reverse voltage because sinusoidally, if you see the Zener breakdown of this voltage of the particular diode, I say you have selected a diode whose VD max, maximum supply voltage is plus or minus 10. That means is Zener. They call VZ. Correct? VZ is the Zener breakdown, reverse bias control will be greater than 10 volts. That diode you have to select. If you select diode whose, for example, Zener diode is breakdown 8 volts. If you apply 10 volt reverse, then it will become a Zener diode. It will start conducting. That's not allowed. So that is what you have to do. Thank you. You understood?
Thank you. Yes, sir. Thank you.
So generally, if I say my diode is a 30 volt diode, I said 1N7001, they say maximum VD can be plus or minus 30 volts. That means if you see is VZ of this diode, maybe 40 volts. It will not be 30 volts. If it is less than 30 volts, then it will become a Zener diode. Reverse bias conduct, you cannot use it as a rectifier. The many diode, if you see data sheet of that, they may give VZ. Zener may not give it also. But it is automatically understood that is Zener breakdown voltage above in the reverse direction. It may break down at 40 volts and heavy current will it will blow. The diode will be burn. So that's why you should apply only the AC voltage, DC voltage, reverse or positive. It will be same as what the manufacturer 30 volt, 100 volt, 200, 500. That's what you have to use. Okay, thank you. Okay, we were talking about rectifiers yesterday. Okay. Yeah, we stopped here. Correct. We are talking about IDC. Now I just wanted to continue and complete this today quickly. Whenever I talk about this one, I told you we can draw the waveforms. So another few more things I want to explain using waveforms. Okay. Please see that this is a sinusoidal voltage. I could not exactly draw. So this is one cycle, first cycle. This is second cycle. First cycle. This is the second cycle, and it can repeat as it is. This may be third cycle. We say this is called here generally AC voltage called a periodic waveform. correct? This is the period equal to 1T, capital T. It will have one positive, one negative. Okay, same thing repeats. So that's called periodic cycle. Generally, AC voltage like that only. It can be sinusoidal. See, please note that periodic waveform means it need not be sinusoidal. It can be square wave also. It can be triangular wave also. Any waveform which has positive and negative equal magnitude, same shape is called a periodic. So we have our grid voltage, this one. The job of the half-wave rectifier, that is nothing but diode job is convert this is called AC voltage. This AC voltage should be converted into DC voltage. What what it is going to do, it is not going to generate pure DC. Please remember, the rectifier circuit, whether half wave, full wave, bridge rectifier, or this one, it is not going to generate pure DC, diode alone. For that, we need additional filter. We'll see that. Now that I have this one, this is input, correct? This is input waveform, which is supplied to diode. Diode will conduct only positive half cycles. Okay. So if you see after the anode, so this you are supplying to anode of the diode. Already we know the diode circuit, the rectifier circuit. I will just show that this is the transformer, secondary. This is the primary. I am supplying AC voltage. Correct. 220 volts I supplied, 50 hertz. And this is the secondary. This is called VP. This is VS. This is connected to diode rectifier through load resistance. This is diode, anode, cathode, RL. This current is called IDC. Same current is flowing to the load, so it is called as IL. And this is VL. And so this current will be flowing like this. Correct? This is the IL, IDC, all are same. Correct? Even IS, secondary current, IS equal to ID equal to IL. Why? They are all connected in series connection. According to it is series. So same are this one. Okay. This is my half-wave rectifier. Single diode. Why it is called? It will conduct. What will be the output of the here? If I measure, so this is the voltage applied. This is the voltage. This waveform is given from the transformer secondary. What I will get? Secondary voltage like this. Same voltage only. Okay. I may not be able to exactly draw. I'm not a drawing master. So I just I engineer. So I'm trying to. So that means this is the voltage at the cathode of the diode. This voltage, if I measure oscilloscope connected to that, this will cut. So you will see only positive half cycle load. Okay, there is a small mistake here in this second half-wave rectifier output. Can anybody say any idea in electrical background? I made a small mistake is that you can say that. I say that this voltage is, for example, Vs equal to 5 volts. I gave 220 volts. It is a step-down transformer. From 220 volts, it is reduced to 5 volt. Correct? It is possible. Correct? That means secondary turn 2 less compared to primary turns. So that is step-down transformer. I am getting the AC voltage. This is the secondary voltage. Correct? This is secondary voltage. This I say that 5 volts. Right? So this is 5 volts. This is negative 5 volts. Any idea? There's a small correction you can do. Second, this cathode voltage. This is called V diode. V diode, that means at the cathode terminal.
Sir,
Small.
V diode maximum should be 4.3, sir.
If you tell only, you learn. Nothing wrong. Don't worry, hesitate. See, if you want to learn, don't worry about classmates. Hey, they are sitting this one, he will tease me. You don't know this like this. This is what makes students sometimes not to learn. If you have doubt, ask. I always say when I studied, I am telling you, it is not that boast myself. That's I ask any doubt in the class, or the BTech, MTech, PA, any class if I have doubt, ask teacher. Let others think whatever they want. I am not bothered. I want to learn. You tell me, somebody want to tell something after they kept quiet.
Sir, VD max should be 4.3 volts.
Yeah, no. The VD max will not there. See, you know that the voltage in the, you apply in the anode, put in another color, you will see clearly. Increasing, zero, whether the diode will conduct even in the forward bias condition up to this position, correct? For this time, the voltage is less than 0.7. So that means the diode will not conduct. Again, once diode reaches 0.7 volts, now it is forward bias. From here, it increases to 2 volt, 3 volt, 4 volt, 5 volts. Again, it is decreasing. This is the peak voltage, correct? 5 volts, positive peak. Then it is decreasing. When it comes here, what happens? Now it is become, sorry, this is again 0.7 volts. Please note that plus 0.7 volts only. This period, it is 0.6, 0.3, 0.4 like that is reducing. No, this is zero. What will happen during this period? Diode won't conduct even in the forward bias. So what should be this waveform? This waveform should be drawn like this. Let me clear it. Then you will. Waveform should be for some people a dotted line. Then it becomes state. This is again for the entire period it won't work. Again for this. That is called cutting voltage, correct? This is 0.7 volts. Less than during the period, it won't conduct. So what you will get is, yes, like this. Again, it won't work. During this period, it won't work. Sudden rise, then comes this one. You can see this is how it will be. So this period, you can see here, everywhere this period is there. Correct? It won't conduct. So this is what actual output is going to do. Okay. Now that it come, what will be the DC? This is called please note that this is called a pulsating DC. Note down. Pulsating DC voltage. Not DC voltage. DC voltage means how it should be? With respect to time, 0 to time is going infinity. The voltage should remain constant. This is 0 volts. For example, 12 volt battery. Correct? If you are not connected with load, you take your lead acid battery, the voltage should remain constant. Correct? If you measure now, after 1 hour, 10 hours, tomorrow, 10 days. Correct? The voltage will remain constant every time instant. This is 1 hour, 2 hour, any time measure. If it remain constant, then only it called a DC voltage direct. It's nothing. The voltage remain constant. Correct? But here, the voltage is not constant, but it is called as a DC voltage. I already told you, as long as voltage doesn't go to negative side, with respect, this is 0 volts, correct? With respect, this is positive voltage, correct? The voltage is going only in positive side. It never comes to negative. So this is negative voltage. Input here, positive and negative voltages, but output of the rectifier. This is the output of the rectifier. Who is rectifier? The diode. The diode output is a pulsating DC. Voltage is always one-sided. It goes 0 to 5 volts. Comes down. Again, remains 0 for negative cycle. Again, 0 to 5 volts. Correct? Positive side, it is same as your input because varying signs are in it. When during negative side, 0 volts. So, never comes on negative side. Negative voltage. Correct? 0 to minus 5 volts or whatever be. So, here there is no voltage. Always positive side. If voltage is increasing one side alone, 0 to 5 volt, it can be sinusoidal, it can be a triangular, correct? Or it can be square type, correct? All these things are called a pulsating DC voltage. The voltage always above 0, it can go up to infinity, plus infinity, or it can go like this. Or, correct? It can give a gap, something like this, or a square wave, 0 to minus side. This is also called a pulsating DC because voltage is observed. Varies from 0 to some negative, never go crosses 0 line. So in this case, what I said is this voltage output of your diode or rectifier circuit is nothing but pulsating DC voltage. Correct? So that is called as rectification. The process of removing the negative side of the AC voltage. Correct? Negative voltage, this one is, and allowing only positive voltage appear to the load. Where it goes, the voltage. The load coming, this voltage is applied across this one. Load resistance. So the load receives pulsating DC voltage. Okay. So it since this, if I use only single diode, if I use only single diode, if I use only diode, the output will be only input and pass during positive cycle alone, output a negative cycle 0 volts. So that's why it is called as half wave rectifier. Only positive half side will be appear on the load. Remaining negative will be stopped by the blocked by the diode. So this is called as half wave rectifier. Okay. Now, and this what output? The output is a pulsating DC voltage. But I want what is the average voltage? Average voltage means you have to take one full cycle. This is called a one cycle. There is a 0 to 360 degree. During the time, positive half cycle will also vary. It is not constant. It is varying. Negative 0. That means to find out the DC, VDC, correct? This is pulsating DC. VDC is nothing but integrate this waveform. Which waveform? The entire half wave rectifier voltage for this entire cycle, correct? 0 to, this is called as 0. Generally, when we talk this one, pi, 180 degree, correct? This is, pi by 2, this is pi, correct? So no, we start with, 180, yes, yeah. I want to use common terminology. 0, after that, this is 180 degree. That is nothing but pi, correct? So this is 360 degree. 180 is negative half cycle 0 volts. During this is varying. If I integrate 0 to 2 pi, that is one cycle. This is 2 pi, this is pi, correct? And whatever that, V pulsating DC. I say PDC with respect to DT, and supply upper and lower, you will get a constant DC voltage. The constant DC voltage I can represent in another color. Okay. Correct. So because this is the VDC, which is nothing but this can be computed using this. They are called as average V average voltage. There are some books they call V average voltage. Some books they call as VDC voltage, which is nothing but you can compute like this using this formula. Okay. So that is called as average. What is VDC? If you substitute this, it will be equal to VDC. Note down, VDC will be V peak divided by pi. For half wave rectifier, VDC equal to V peak. Correct? V peak divided by pi. For example, if I say my V peak equal to 50 volts, okay, I use half wave rectifier. What will be my DC voltage? DC voltage means area under the curve if is integrated. Correct? This is called as VDC. VDC equal to V peak 50 divided by pi is nothing but 50 divided by 3.14. So many volts you can compute. That will be that voltage. The value will be this much. It will not be. So this is 5 volts. VDC will be this voltage. You can note. You can compute from this. Okay. So this is how the half wave rectifier works. Next thing is there are some other things we need to consider when we talk about half wave rectifier. Okay. One thing is what we call a voltage regulation of the half wave rectifier. Voltage regulation of half wave rectifier. Correct? How it is now? I have, for example, understanding that first thing is we can to understand what is voltage regulation. I have a power supply, which is DC power supply plus minus, and this power supply is, what is the power supply? DC power supply. This one, this VDC, correct? V average, we are calculating on this one, correct? So we know that this is nothing but VDC or V average is nothing but V peak divided by pi for the half wave rectifier. Please note that this is a equivalent circuit of a AC volt. What we are supplying AC only, correct? And that is rectified by the diode. Then it is supplied to load. Now this circuit can be replaced by this circuit. This is called as equivalent circuit. I can call this as equivalent circuit of half wave rectifier. Is VDC. That's why I believe this VDC is nothing but V peak divided by, already I am computing. If V peak varies, this VDC will vary, pi is a constant. Now this is connected to load, but one more thing is there, and this is connected to load, my load resistor RL. This is nothing but RD, correct? RD. What is RD? RD is nothing but diode resistance. Diode, D represent dynamic resistor. Okay. RL is load resistance. Okay. Another thing also is there. Please note that we have the secondary coil, correct? Secondary coil or transformer only supplies the AC voltage to the rectifier circuit. So this secondary coil also has some resistance. I see that R secondary coil, R S means secondary coil resistance. Similarly, the primary coil also RP, primary coil resistance. VP is the primary, this one. So there's a current flowing which is called IP. That we need not worry about it. Okay. Right now, that means here we need to add. This diode resistance, diode dynamic resistance. This is load resistance, correct? And now, what is now, because of there's a current flowing, there's a current flowing. We say that IS is nothing but the current supplied by secondary coil should be equal to ID, should be equal to IL, VDC, RS, RD plus RL, right? So according to IL is being, so this is equal to IS RD or IL series, currently glowing series. You can compute using this formula. Okay, using this formula. Okay, this is how to compute the load current. Okay, we are talking about voltage regulation. We know that now that I have connected load, for example, my load resistance is equal to say 10 ohms. Okay, the dynamic resistance diode equal to 0.1 ohms. For example, understanding for easy, I say 1 ohms. Okay, the coil resistance also 1 ohms. Take it granted for easy purpose. So, what is the voltage? I said we are applied 5 volts. Correct? V peak I said 5 volts. Okay. Then what will be the VDC? VDC equal to V peak divided by pi is nothing but 5 divided by 3.14. Somebody can tell the value? Okay, let me calculate. 5 divided by 3.
1.59, sir.
1.59. We can make it 1.6 easy. Okay. So this is going to be VDC is going to be 1.6 volts. So the average voltage. But peak, please note that peak voltage supplied by the transformer is 5 volts. But average DC voltage, I say that VDC is going to be 1.6 volts. This is what is supplied to this. Okay. Now, how to calculate this one? IS or IL load current. My interest say what is current flowing to my load, correct? That is same as this one. I can say IL equal to VDC divided by we can substitute the value. There's no 1.6 volts divided by RS equal to, I said, 1 ohm plus RD, dynamic resistance of the diode, when diode is conducting. Whether now diode is conducting or not.
Yes, sir, it is conducting
How?
because it has already rectified in one direction.
Huh? Tell. No, well,
Hello?
correct. So,
So
unless
it
you tell,
is-
you won't learn.
It has
Huh?
already rectified in one direction. So
No, rectify
conducting.
happened when my input secondary voltage crossed the 0.7 volts. I am applying my input voltage varying from 0 to 5 volts. Please see that 0, 1, when up to this you won't conduct. Once it crosses during this period, the diode is conducting. Correct? So conducting forward bias. Forward bias happens only when the input voltage greater than 0.7. My input voltage is 5 volts. Correct? It is increasing 0, 0.1, 0.2, 0.3, 0.7. The output will be 0. If you see diode cathode, the output will be 0 volt. That's what I represented. Correct? Till it reaches 0.7, 0 volts. Even though you're applying 0.5, nothing happens. Cathode. The load also no voltage, no current. Once the input voltage crosses 0.7, diode start conducting. Again 5 volts, 4.5, 4, 3, 2, 0.7 to 0.6, again 0. Negative also absolutely no current because the reverse bias. Same thing happens, correct? So because of that, we need to say here, that's why we applied the 5 minus 0.7. That is what the applied voltage. But instead of that, I can use directly VP. VP is 5 volts, correct? So if I use a different voltage, say 100 volts voltage, that is 100 divided by 3.14 will be VDC. Now, I want current is nothing but VDC for the entire cycle. That is what going to be there, divided by total resistance. This is RS, this is RD, RL. Correct? So that is 1.6 divided by 12. So that is the our current going. Correct? It will be milliamps. Correct? It will be less than amps. It will going to be in milliamp. 1.6 divided by 12. So you can compute the load current. Now, one thing what we notice, if load is varying, I said my load value equal 10 ohms. Correct? My load ohms remain this one. Diode over this. My the going dynamic is going to be constant. Note down, actual RD value. RD should be equal to delta V D divided by delta ID. Okay, the ID is a current. So you can compute the visible, screen visible.
No, sir.
Sir, no,
Screen
it's
is
not visible, sir.
Yeah, just now I know, I saw that.
Screen is not visible, sir.
Yeah, current went and came, fluctuation. But since I have UPS, it work by the internet disconnect now.
Screen is visible, sir.
No screen is
Okay.
visible, sir.
Okay, so this is how you compute. Okay, so the dynamic resistance can be computed using this. Generally, it is going to remain constant because VD will be around 0.7 unless otherwise some extraordinary cases doesn't change. That's one thing. Next, our voltage regulation we are talking. If I supply a voltage from a power supply, DC voltage, this is my VDC. VDC we have computed for 5 volt secondary, it should be 1.6 volts, correct? This is 1.6 volts. 1.6 volts, this is 0 volts. This should remain constant. It will remain constant as long as my load is 10 ohms. Suddenly, I increase my load to 0.2, reduce my load to 0.2 ohms. Correct? So, if I change it, what will happen? The voltage will fall. Correct? The VDC This is called VL, correct? Which is the voltage according diode. Will, if depending on load condition, it can fall also like this. Okay. This is called as voltage drop. It is not remaining constant, correct? If I increase the load, it can change. Instead of this, it can change this also, dynamic condition. Okay. So this, okay, is not acceptable. Voltage drop is not acceptable. What I want to have constant DC. Okay. The word. So if there's a change in the output VDC by the rectifier change, then I say that it is called as this one. That's this one we call the percentage of voltage regulation. Take the formula. Percentage of voltage regulation is nothing but V no load condition. This is V no load condition. No load condition voltage is 6 volts. Now I am connecting load. If I change the load, RL is varied from, for example, 1 ohm to 10 ohms. The varied from 1 to 10 ohms. Then the VDC can fall like this. Correct? So this is at 10 ohm condition. When RL equal to 10 ohm condition. Correct? So at this is RL equal to, for example, I say that 5 ohms. And this is RL equal to 0 ohms or 0.1 ohms. Very 0 is my short circuit as a 0.1. If I vary this, you can see that the voltage is dropping. Correct? As I increase the load, this one, my voltage is dropping. This is 1.6. Sorry, this is 1.6. But if I increase load, this is called a voltage drop due to load change. The voltage follows this one. So the voltage regulation, I can say voltage regulation. What is time? If time is up, please tell me. Sometimes I'll be just to, don't hesitate to tell if time is up. Because you need to catch your bus, all those things. So voltage regulation equal to no load voltage. Voltage at no load minus voltage at full load divided by voltage at full load. Correct? So for example, for this condition, this is V no load. What was this? 1.6 volts. Now I will decrease the load resistance from 10 ohm, 9 ohm, 8 ohm, because I am decreasing. So for example, when it becomes load resistance equal to, I say for understanding also 1 ohm. Okay, 1 ohm. That time it reduced to, for example, 1.2 volts. Correct? Then I can say that 1.6 volts minus 1.2 volts divided by 1.6 volts multiplied by 100 is the percentage of voltage regulation of this rectifier circuit. Correct? You can say that this will be 0.4 divided by 1.6 into 100. Somebody can say how much it is if you have a calculator.
%25. 25.
So percentage will be 25%. Correct? This is called a poor voltage regulation. I can say that this should be smaller in number. 0 is very good. That means if I increase my load 10 ohms, sorry, decreasing 10 ohms, 9 ohms, 8 ohms, 10 ohms, I go 1 ohm. Still, the voltage is around 1.6, close to 1.6. Then my percentage will be better. Correct? So voltage regulation should be at least 80 to 90%. So here it is a poor regulation, you can say. Okay. So this is one of the important parameter. Then next thing is what we want to do, ripple factor. Already we talked about this one. Did we talk about ripple factor yesterday? Gamma I talked, correct? No? Rectification ratio we talked, if I am correct. Correct? Previous class, yesterday, we talked about rectification ratio.
Yeah, rectification we discussed, sir. Ripple factor I didn't remember.
Ripple factor. Ripple factor RF equal to, you can compute using ripple voltage divided by VDC or V average. Please note that already you know VDC or V average is computed with V peak divided by pi. Correct? Already we have V peak divided by pi. Already we know this is ripple voltage. What is ripple voltage? Correct? So you can see that my voltage is pulsating. The pulsating is called this voltage is called a ripple voltage. Later, when you use a filter, I will tell you what is ripple voltage. Use a capacitor to reduce the ripple. Ripple is nothing but wave. Correct? For example, if you go and sit in front of a beach, we say waves are that is called ripples. Which something is varying, which represents a flat surface up and down, which average this one that is called ripple. So the voltage coming after the rectifier is varying. This is called ripple. Ripple voltage, correct? Voltage divided by VDC is called as ripple factor. Smaller the ripple factor is better. Okay, please note down. So how will you calculate? The ripple factor can be calculated using VRMS of ripple voltage. Next class, I will give some examples. Then you will understand. VDC. So ripple factor can be calculated using this formula. Okay. For half-wave rectifier, correct? Ripple factor. For half-wave rectifier, note down this form. This is what I want. Half-wave rectifier. The ripple factor RF equal to root of IRM square, IRMS divided by IDC. See, this is in terms of voltage. Please note that ripple factor can be calculated using in terms of voltage or by current also. So that I am giving two formulae, right? So IRMS divided by IDC whole square minus 1. This formula you can note down. So we know that IRMS equal to IP divided by 2. Okay. So in this formula, the IRMS can be calculated using this. Already we saw IDC, correct? What is IDC? Just now previously we calculated IDC equal to VDC divided by RS plus RD plus RL, correct? We computed, correct? VDC we computed 1.6. We divided we got a point something. What is the current we talk? Load current somebody is 1.6 divided by something.
0.13, sir.
0.13 amps. Correct? So in this formula, this is 0.13. Sorry, 0.13. You can substitute here. IRMS can be computed using RMS voltage. RMS voltage is the AC voltage. Correct? The DC voltage. We know that RMS voltage is nothing. If I say V equal to 220 volts, okay, that is called actually VRMS. This is nothing but VRMS voltage of this one. Here, what is my VRMS in this example? We said VRMS equal to one more thing also. Here, we said peak voltage equal to V peak equal to 5 volts. Positive. Similarly, minus V peak equal to minus 5 volts. Correct? These are called peak voltages. How will you calculate RMS voltage for this? RMS voltage equal to V peak divided by root 2. Okay. RMS equal to V peak divided by root 2. You can find out. Okay. So similarly, if I know IRMS, if I know I peak, if I peak is known, correct, you say for example 1 amps, I can find out IRMS equal to I peak divided by root 2. Here you can use that formula. Okay, this is I peak divided by 2. Should be not 2. Should be root 2. I will check up. It should be root 2. If I am correct. Because many times we are calculating many things, so remember. So IRMS, you can substitute this value here, and IDC you calculate, VDC you know, you can calculate IDC using this. VDC formula already we have. From that, substitute RS, RD values are given, you can compute this one. So you can expect simple problems, okay, in the exam, in some exam. And before that, another two more factor I want to talk in the half wave rectifier. After that, we go to full wave rectifier. So rectification ratio. Did we talk about rectification ratio? No, correct? Okay, next parameter rectification ratio. See, these are all important parameters to decide whether use half wave, full wave, this one. This is well known, but for understanding, we are teaching this. Rectification ratio, I can say that RR equal to DC power to the load divided by AC power to the rectifier. Or we can say the input AC power. Input AC power. Okay. So this is formula. So this will be written as PDC divided by PAC. Okay. What is PDC? PDC equal to rectification ratio equal to PD. PDC equal to VDC multiplied by IDC, which is nothing actually V average multiplied by I average. Same. Because some books they put DC or IDC, some book they put average value. Already we know the formula. Okay. So once using that, you can calculate. And what is the PAC? PAC equal to V supply multiplied by I supply. Okay. That is called PAC multiplied by cos phi. What is cos phi? Cos phi is called a power factor. For AC, we have to talk about power factor. For all our understanding purpose, we can take it as 1. Correct? But generally, the power factor of the supply, what you are getting is 0.7, 0.8, something like that. The value will be around 0.7, 0.8. 1 is better. Okay. So for our purpose, we say that this is 1. So in that case, we can remove the this part. VL, you can say that secondary voltage multiplied by secondary current. That is PAC. That you can calculate. Once that is known, automatically you can compute this from using these two values. You can compute the rectification ratio. One small thing, just few minutes. Another thing is what you call a transformer utilization factor. Okay, they call shortly TUF. TUF equal to DC power supplied to load. Whole thing divided by AC rating of the transformer. Transformer secondary coil. Because secondary coil only, we are supplying 220 volts in the primary. Secondary coil step down, I said it is 5 volts, correct? From that, always use a secondary coil. Okay. This generally can be written TUF is written as PDC divided by PAC. Okay. PAC secondary. This can be expanded in terms of current. TUF can be, this is one formula. Other formula, TUF can be written as IP square, note down, I peak square divided by pi square, okay, multiplied by RL. The whole thing is divided by V peak divided by √2 into IP divided by 2. Okay. We know V peak voltage, IP is given, IPK is given, and pi is 3.14. And here also this one, RL load resistance. If you are given with the load resistance, correct? And I peak and V peak, then you can calculate transformer utilization factor. Okay. And lastly, further simplified formula. You can note down both the formula. The TUF equal to 2 into root 2 divided by pi square, whole thing multiplied by RL divided by RD plus RL. Okay. This can be further simplified. Last formula, TUF can be written as 2 into root 2 divided by pi square. That means we can neglect this if RL is much greater than RD. What is RD? Diode resistance. I told you the diode resistance will be in the order of 0.01 to 0.1 in case of power diodes. In power diodes, correct? The RD, dynamic resistance, this one can be 0.01 ohm. And if current is very high, for example, 200 amps, 300 amps, RD can be even 0.001 ohm. Nothing, right? The milliohms. If very heavy. Otherwise, RD is bigger means lot of power will be dissipated in the diode resistance. But generally in the order of 0.01 like that will be there. Most of power which is 20 amps, 30 amps current rating, right? Very high, it can be less. So if this is less, my load resistance equal, for example, 10 ohms or 1 ohm, correct? My load for the understanding say the 1 ohm. The point, what is the ratio? 100 times lesser. In that case, I can neglect this part, correct? If I neglect this is gone, then it will become RL divided by RL can be removed. So I will end up with this. Note down this formula, correct? So both these formulae in the exam, depending upon what parameter, whether you are getting correct T of the both the formula you note down. Okay, so this is final formula. I stop here. So if after rectifier in the exam, you can expect draw the after rectifier circuit and the voltage input voltage is supplied. Transformer is given. Transformer ratio is given. Transformer input voltage 220 volts. Transformer ratio step down transformer. Step down transformer is 25. Correct. Then we get VS secondary voltage equal to 220 multiplied by divided by 25. Correct. That much will be less. 220 divided by transformer ratio will be the secondary voltage. From that, if they are you can compute peak voltage. That is VRMS. That is secondary voltage. The VS is nothing but RMS voltage. From that, you can calculate V peak. Then you can do these problems. Right? You can expect the half-wave rectifier. You will be asked to calculate voltage regulations, correct? Then RF, correct? Then ripple factor, the rectification ratio, TUF. This may be asked to compute. Maybe 3 to 4 marks will be a problem in NSEM exam. Okay, I'll stop here. See you on Sunday, 10 o'clock, correct? You want exam by 10 o'clock, correct? NSEM, the midsem exam.
Sir, Saturday, right?
Saturday or Sunday?
Saturday, sir.
Because Sunday we have the other subject exam.
Oh, you have exam, huh?
Yes, sir. We have the other subject, Anand sir's
Which
exam
subject?
schedule.
Oh, okay.
Anand sir's exam.
No, if you want, I can conduct next week also. I don't want to know to listen. You have to prepare. Please note that it is 30 marks. Okay. If you want, I can change next Sunday also. Please note that portion is remains same. I am not going to increase same.
Okay, sir. Okay, sir.
That will be great, sir. Sir, you are
That will be great, sir.
Sir, you are so
That will be
kind,
great,
sir.
sir.
I'm really, sir, awe of you, sir. You are so kind, sir.
Okay.
Thank you. Thanks
so we'll put on next Saturday. Let them write this exam well. Prepare well. Try to get maximum. Your midsem exam next Saturday. Oh, okay. That
Sunday.
is what day it is?
Sunday, sir.
Sir,
Tell me.
Sir, because of this exam schedule, my company planned one business travel on Sunday, on the next Sunday, sir.
Okay, Saturday. Next Saturday.
Next Saturday should be fine, sir.
Okay, next Saturday we'll have. Okay, so because I know about you, you are doing working and preparing. I always more considerate for VMS student compared to regular students. Okay, next Saturday, okay, instead of this Saturday.
Okay,
Yes,
sir.
you have to say
sir.
yes.
Yeah.
I-
Yes, sir.
Yes,
Yes.
sir.
Yes, sir. Yes, sir.
Okay, next Saturday will be your mid-segment exam. What time? Tell me the time.
Second of the.
Sir, 10 to 4. Second half or first half? Which one?
10 to 4. You want to write the exam? 4 hours. Anna Sam said 10 to 4. I will give you an exam. Don't worry. Some design
No,
problem.
sir.
You can do whole day.
No, no, that's-
People so much.
Sir, morning 10 o'clock or afternoon 3 o'clock? Anyone is any
Oh, no, you tell me now. All are there. You tell.
Maybe afternoon 2 o'clock we can have this. Have it.
Generally,
If
why
everyone
hard
is okay.
Sunday, hard Saturday? Generally, do it morning. My advice. I am not. See, I am sitting inside the AC
Yes, sir.
room.
Morning is fine, sir.
Morning 10 to 11:30, 1.5 hours. Okay.
Okay.
Next Saturday. But
Thank you for considering, sir. Yeah.
No. Yes, that is very important. But you have to do well. I will ask Anand, how did you do your exams?
Sure, sir. Sure. Yeah.
If
Sure,
you
sir.
don't
Thank
do
you for
very well in the
considering.
Anand exam, I will reduce 10 marks for everybody.
No, sir, they will do better, sir.
Yes. Okay. Thank you. See you on Monday evening, 6 o'clock.
Sure,
Sir,
sir.
Monday,
Thank you.
sir,
Ah.
sir, Monday Ramzan.
Okay. Monday
I-
leave and Tuesday, Wednesday, Thursday.
Okay, sir.
Okay.
sir.
Monday,
Thank you, sir.
Thank you so much.
Okay. Take care. Enjoy your Ramzan holiday. But this group has to write exam very well. That is most important. Okay.
Thank you, sir.
Sure, sir.
Thank you.
Thank you, sir. Thank you.
Okay.
Thank you, sir.
Okay. Give your